Vector calculus, visualization of fields and operations. In this video, I am not going to be showing any math equations. The purpose of this is to just try to visualize a scalar field, a vector field, and then operations on those fields, things like gradients and divergence and curl. So let's dive right into this. We start with a scalar field. First, field is not necessarily a field in the electromagnetic sense. That's really a mathematical word, meaning that something is a function of position. So a scalar field is a scalar quantity, so it's just a single number that is a function of position. So if we were to plot those, they would look like a cloud or a fog, and it's not really missing any information. Now, a vector field is a vector quantity that is a function of position. And remember, a vector is carrying two pieces of information. It carries the information of a scalar field and its magnitude, and it also conveys a direction. And so when we're drawing vector fields, very often we use what's called a quiver plot, and we just draw a bunch of arrows. The length of the arrow is conveying the magnitude, and of course the direction of the arrow is conveying the direction. So vector fields really contain twice the amount of information of a scalar field. And so we have scalars and vectors. We can visualize a vector field maybe slightly differently, and hopefully this is not too confusing. But in addition to the magnitude of the arrows conveying magnitude, we can give it a background where the color is also indicating magnitude. Sometimes you'll even see this where the magnitude of those arrows are normalized, so that all the arrows are the same length, but the color in the background is conveying the magnitude. And which one's better? Probably just depends on what you're visualizing and what happens to look better at the time. So just be aware that sometimes vector fields are drawn this way, and it's not implying necessarily that there's also a scalar field involved. If there is, they'll tell you that. There's what's called isocontour lines. If color here were representing elevation, for example, sometimes you'll see these isocontour lines on topological maps. And what they represent are lines of equal elevation. So if you walked along one of those lines, you wouldn't have to walk up or down. And of course, where those lines are squished together the tightest, like right here, that indicates where this function's increasing the most rapidly. So we can form isocontour lines within a scalar function. Now our first operation. Here we start with a scalar field, and we would like to calculate the gradient of this scalar field. And really the gradient is the multi-dimensional equivalent of a derivative. So somehow we are assessing how quickly this function is changing. But now there's also a direction associated with that change. So let's go ahead and calculate the gradient. In this case, the color in the background is not indicating the magnitude of the gradient. That is solely represented here by just the black arrows. The color in the background is the scalar field from which this gradient was calculated. So the gradient is a vector field. It's indicating two different things. The magnitude is really conveying the steepness of the hill. It's telling us how quickly the function is changing. And the direction of the gradient is telling us which direction has the maximum change. So again, if we were looking at an elevation map here, the gradient is pointing uphill towards the highest value. Now the gradient operation is sort of dumb. It's kind of like if it is the slope of the hill, it's like when you're looking at your feet and you're trying to get to the top of a mountain. You'd like to walk in the direction straight toward the peak, but you're sort of dumb. You're just looking at your feet. You don't see macroscopically where the peak is. All you can do is try to determine uphill looking straight down at your feet. And the gradient is that way too. it doesn't point to the maximum value anywhere. It's just a local assessment of the slope at a specific point, and it's just sort of locally pointing uphill. So think of gradient that way. Now, if we look at our gradient and scalar function and the isocontour lines all at the same time, what we see is the gradient is always perpendicular to those isocontour lines. And that makes sense. Those isocontour lines are traversing where the value of that function is not changing at all. So it makes sense then that the direction of the gradient will be perpendicular to that, since the gradient is calculating the direction of maximum change, so as always to point towards increasing values or pointing uphill. Now on to divergence. The divergence only makes sense if we start with a vector field. So we're starting with a vector field here. And if we look at this long enough, we can see some peculiar things. There's regions, for example, where I have the cursor circling right now. It seems as if this particular vector field is emerging from that region. Also over here, there seems to be a tendency for the field to be converging on this point. And in fact, divergence of a vector field is the tendency of that field to look like it is emerging from a point or converging to a point. So when we calculate the divergence here, we expect to see the highest values on top of these points where the field is diverging or converging. So let's look at that. Let's look at the divergence of a vector field. And the divergence, by the way, is a scalar quantity. The direction of divergence does not make any sense. It's just the tendency of a vector field to converge to a point or diverge from it, and so the direction doesn't make any sense. So divergence is positive when the vector field looks like it's diverging from a point. So we see positive numbers in regions where it's diverging. And the point where it's diverging from, of course, that's where we'll see the maximum divergence. And that's the color in the background. Then where the vector field appears to be converging, we get big numbers, but they're negative numbers. That's sort of negative divergence, or you can think of it as convergence. So that's the divergence of a vector field, and it is a scalar quantity. And it's calculated as the dot product of this del operator and the vector. The next operation we'll talk about is curl. This is an operation performed onto a vector field, and it calculates another vector field. The curl of a vector is the tendency of that vector field to rotate about some axis. And if we look at this vector field long enough, we can actually see several areas where this field appears to be rotating about an axis. For example, my cursor here is tracing a line, if you will, in the vector field that appears to be rotating about an axis centered right around here. And I can pick out others. Here, it's rotating the other way, but it seems to have an axis right around here. So we would expect the curl to have the largest numbers around those axis of rotations. Let's go ahead and calculate the curl. Here we can only see the magnitude of the curl, but because our original vector field is completely in the plane of the screen, that means the direction of the curl is completely perpendicular to the screen. The red areas indicate the direction of curl coming out of the screen toward us, and the blue areas, it's going into the screen away from us. And there's a handedness. If we take our right hand and we curl the fingers along with the original vector field, our thumb will point in the direction of curl. And we could also do that here. A little bit awkward, but our thumb is now pointing into the screen. So the curl is the tendency of a vector field to appear as if it's rotating about an axis. The magnitude of curl tells us the strength of that rotation, And the direction of curl is telling us the axis, the orientation of that axis about which the field is rotating. So here's a nice summary which tells you what inputs these operations have and what outputs they give us. So for example, we look at our operation, addition and subtraction. They take as inputs vectors, and so if we add or subtract vectors, we get vectors out. Dot products, they take as inputs vectors, and they give us a scalar as an output. Cross products takes inputs as vectors, and it outputs a vector. The gradient has an input of a scalar function, but it outputs a vector function. Divergence takes as an input a vector function and outputs a scalar function. And last, the curl inputs a vector function and outputs a vector function. So in doing math, having a table like this either written down or memorized is a really good self-check. For example, if you calculate the curl of some vector function and end up with a scalar, clearly there's been a mistake made somewhere.